Okay, so the topic is they are going to talk about rigid motions. And of course, the idea behind this, well, it's pretty natural. Say, for instance, you have a plane, and you have an object on the plane, whatever picture you have, and say you wanna move it. You wanna move it, right? You wanna sort of maybe rotate it or shift it or reflect it. Yes, and the property that you want to preserve, well, you want to preserve that smiley face, right? After you sort of move it, you want to say still have this nice smiley place, right? And one may wonder what kind of movements you're allowed to do in order to preserve this smiley face, without. So basically, what we want to do, we want to keep the distances between points. On our plane, right? We want to keep distances and say configurations, angles, right? Okay, and one may wonder what kind of linear operator can we use, because linear operator, well, it gives us certain map, certain assignment, certain movement, if you wish, right? You move a point to another point, that's your sort of map. And one may wonder what kind of linear operators we allow to have. Well, so here's a basic definition. Since we are looking for a linear operator which preserves the distances, right, that would be natural to define the following. So let V be an inner product space. Well, a function, a map or a function f from V to itself. So this function f plays a role of motion or movement. A function f is called a rigid motion or rigid movement if, well, it preserves the distances between objects, between points. If we compute the length of fx minus f of y, right, you have 2 points, and then you apply f, you get another 2 points, and you want to have the same distances. Yeah, want to keep the distance. So this distance has to be the same as the original one for all x and y from V. Yeah, this is a key property that one would like to have. And well, there are a couple of obvious examples. I already mentioned them right here. Yeah. So what can we do? Well, first of all, any isometry. So isometry operator T gives an example, provides an example of such a rigid motion. So any isometry operator T. Well, why does it the job? Well, it's because, well, let's just look at the difference. T of x minus T of y. Then this is a linear transformation, linear operator, right? So you can just put x minus y inside. And because it is isometry, it preserves the length of vectors. So meaning that T of x minus 1 is the same as x minus y. Yeah? And that's what we want. Okay, so another example. Well, let's look at the different functions. So, well, a function, say rho from V to V is called a translation. If there exists a vector, if there exists a vector by which you translate, say, vector, say, V0 from V, such that your function is nothing else, just well, this is precisely the translation by this vector. So you just move everything by that vector, right? So rho of U is, well, U plus V0. Yeah, so you just add each vector, right? So you just translate in that direction for all U from V. Yeah, on that picture, on that nice picture, say if I'm given a vector, say V0 here, what will happen is that I have to translate, I have to move that picture by that vector, right? So that's maybe I can do it. Well, let's just, so there's a, and I have to keep the same smiley face, right? Okay, so that's a movement by that vector. Okay. Now, well, I claim that any translation, any function like this, provides an example of a rigid motion, is an example of a rigid motion. However, let me stress that, well, translation, so if V0 is not 0, then the respective rho, then the respective translation is not a linear operator. By the way, why it is not a linear operator? Because one of the basic properties fails to be linear, namely rho of 0. Well, if you compute rho of 0, it's not 0, but it's rather V0, right? Because, and this is non-zero. Okay, so now we have two families of two examples, basic examples of rigid motions: an isometry operator, right, and a translation. So now let me give the following fact. Let me state and prove the following fact, which is the following lemma. So let f and g be, say, those functions be rigid motions. Again, one has to be careful here, because rigid motion, there are examples of rigid motions which are not linear operators, right? Like a translation. So we really have to deal with general functions, right? Okay, so let f and g be rigid motions, then so is their composite, it's composite, f composed with g. Yes, so that's clear. So because why? So basically what you do, you first apply g, you move by g, and then you move by f. Of course, if you compose it, if you do this two movements, well, you also get a movement, right? Well, however, we can formally prove this also. Say, well, we can just compute what is f composed with g of x minus f composed with g of y. Don't forget that in order to check that something is a rigid motion, we just need to check this identity. Yeah. Okay, so let's just compute it. And well, so the length of that difference is, we can just write it, we can write it down in a slightly different way, right? F of g of y. And then look, I mean, f was chosen to be a rigid motion, right? So meaning that we can apply this property to f. So what do we get? We get just g of x minus g of y. And at the same time, g is also a rigid motion. So we can apply now this property to g, defining property to g, and then we get x minus y. And that's exactly what we wanted to show, right? Okay, so again, that's pretty important, and that's kind of natural, right? Expect that, I mean, the composite of two movements, two rigid motions, is again a rigid motion. Now let me state the following important fact. Theorem. Well, which basically tells us something which basically describes, well, it's an attempt to describe all possible rigid motions. So the question is how they can be described in terms of some elementary motions or movements, right? Okay, so let F be a rigid motion. Again, of course, everything here is happening on the finite dimensional vector space. Maybe I should mention it. V be an inner product, say inner product finite dimensional space. Yes. And so, so let F be a rigid motion. Then there exists a unique orthogonal operator, a unique orthogonal operator. So here, since we are talking about orthogonal, you probably suspect that I have to choose the field F, the field F to be R, right? So let F be a rigid motion over R. So this is our field. So when we deal with the vector space, we choose R. Then there exists a unique orthogonal operator T on V, and a unique translation G on V. Okay, so on V, right? Such that our rigid motion is a composite of that orthogonal operator followed by a translation. So it's G composed with T. So that's a pretty important fact. Basically, it tells us that these two examples from, well, you can construct any rigid motion from these two examples, right? Because don't forget that the orthogonal operator is precisely an isometry operator over R, over real numbers. Yeah, so this fact is telling us that any rigid motion is a one orthogonal operator followed by the translation. Okay, so let's prove this. Well, so first of all, right, so we are given F, right, an arbitrary, say, rigid motion. And so what do we do first? We define a function. We define T from V to V as, I'll just set it to be, so T of U is set to be F of U minus F of 0 for each U from V. So what we claim is that that such T is a linear operator first, and moreover, it is an isometry operator. So it is an orthogonal operator. T is an orthogonal operator. Okay, so let's check this. So first of all, let observe that t itself. I mean, if you just define a function like this, just taking the difference, t itself is a rigid motion, right? That t is a rigid motion. Well, why? Because in this case, t is the composite. First, we apply f, and then we take the difference, right? So there are two steps. I can't see any writing of the, oops. Do you see now? Okay, I don't know. Okay, maybe it's, okay, good. Yeah. Okay, so, right. So what I want to say is that, first of all, the t that we just introduced, that function t, is a rigid motion by itself. Why? Because it's a composite of f, right? First you apply f, you get f of u, and then you take the difference, you take the translation. And the translation by, well, by that difference, right? By minus f0. So t is a rigid motion, that's good. Moreover, what we also can see immediately, that if we just evaluate t at 0, we'll just substitute here the 0. What do we get? We get 0. So t is a rigid motion. T is a rigid motion which preserves 0, right? And now for every, say, vector u from V, well, let's compute t of u. Let's compute t of u. Well, what's this? This is just, by the very definition, it's t of u minus 0, which is t of 0. And then this is, by the very definition, this is what? This is just f of u minus f of 0, right? And then this is what? This is just u minus 0. Because look, f is a rigid motion. F is a rigid motion, so we can apply the property for rigid motion, then get u minus 0, and then we get u. So in other words, t preserves the length, right? So let me stress. So we just get this. Indeed, we still don't know, right? We don't know yet whether t is a linear operator. We just have certain function, and now we just produce more and more properties of this function. Why did we need the step minus t0? Well, you actually don't, but just to see that it's, well, that's fine. I mean, you can also skip it. You can just write it down immediately here. Okay. Okay, so now, again, I mean, we still have to show that t is a linear operator, right? Okay, so to do this, let's look at the following, at the square of length of the difference of t of u and t of v, of two vectors. And let's just apply standard properties of the inner product, because we know that this is t of u minus t of v, comma, t of u minus t of v. And now we can expand it as usual, right? So what do we get? We can take this times this, minus this times this, minus this times this, and plus this times this, which gives us t of u, the length of t of u square, minus 2, just combine the term, minus 2 t of u, t of v. Don't forget that we are over real numbers, so there are no bars, right? So, and then that's plus t of v, length of t of v square. And now we can substitute, because here we know that the length of T of U is the length of U for any U, right? So we can just write it down as U square, right? Minus 2 T of U, T of V, plus the length of V, well, the square of the length of V. But on the other side, well, we can also express the square of the length of this difference, U and V. And what do we get? Again, I mean, we just write it down as the inner product. And then we expand it in the similar way as before, and we just get U square minus 2 inner product of UV plus the length, the square of the length of V. And, well, look, I mean, we can compare this side and this side, right? Don't forget that T is a rigid motion, so they have to coincide, right? And particular, the length of T of U, yeah, so the length of T of U minus T of V coincide with the length of U minus V. And then, well, just comparing this expression, and so this expression must be equal to this expression. So we just conclude that this expression coincides with this expression, right? Or if you wish, I can just write T of U, comma T of V has to coincide with U, comma V. And this, of course, holds for each vector U and V, for all U and V. Again, still, we don't know yet whether T is a linear operator, right? So we just use the properties of rigid motions. Okay. So now the last step. So now we actually want to show, we show that T is a linear operator. Indeed, when we are finished with this, we are done, right? We finish with the proof of the theorem. Why? Because if T is a linear operator, it's already orthogonal, because we just checked it. Well, we just checked it right here, right? Because it's a rigid motion. Okay. So now let me show that T is a linear operator. So we have T of, well, let's just look at the following length. T of x plus y minus T of x minus T of y square. So what's this? This is just, well, we can put the brackets in a slightly different way. Well, indeed, let me just put the brackets like this. So I want to combine these two to one bracket. And then, well, what can I do? I can think about this as one vector, and this is another vector, right? And so I can write it down as the inner product of what? Of, say, of this vector. So T of x plus y minus T of x, right? Minus T of y, comma, T of x plus y minus T of x minus T of y. And then I can expand it, like this is one vector, another, the first one, the second one. So I can expand it, right? I can expand it like I did right here, similar to what I did here. And what do I get? Well, I get again this times this, which gives me the square of the length of this. Minus 2 times, so T of x plus y minus T of x, right? Comma T of y plus, well, this times this, which gives me the square of the length of T of y. And now we can substitute, because, for instance, we know that this t is a rigid motion, right? So we can, instead of this, we can remove t from this expression and from this expression. So we just get x plus y minus x square minus. Then we can expand this expression, 2 of t x plus y, comma t of y, right? Minus 2 of t of x, comma t of y. And then plus, so this expression will give me just the square of the length of y. And finally, well, look here. What do we have? Just here we have just y, right? X plus y minus x is just y. So combining this together, what we get just 2 times the length, the square of the length of y, minus 2. Now here I get what? I get, look, I mean, here we just show that t of u comma t of v is the same as the inner product of u and v. Shouldn't be plus 2. Let me see why it's a plus. No, there should not be plus because there's a, wait, yes, you are right. You are right. You are right, because there was a minus here, right? So I need to put what I have to put here. Yes, I have to put plus, of course. Sure. Thank you. Yes. Now, well, here I get the following. So I get, so this inner product is just x plus y comma y plus 2 of x comma y. I can remove t everywhere, right? And then finally, that's it. That's the end of the story. And now, well, what I can do, I can also expand this, because what's this? This is just 2 of x comma y, right? X comma y, and then look, I mean, here I have plus 2 of y comma y. And then after I substitute, what do I get? I'll just get, well, basically what I will get, I'll just get 0. All of them will cancel. Right? So meaning that, look, have a look here, meaning that we just deduce that the square of the length of this vector is 0. But then, well, if the square of the length of the vector is 0, then the vector itself must be 0. So what is the vector? T of x plus y minus t of x minus t of y is 0, right? And this just implies that t of x plus t of y is the same as t of x plus y. And look, I mean, this is one of the properties of the linear operator, like that t preserves the addition of vectors. Okay. Now there's another property which remains to check, is just t preserves the scalar multiple. But, well, this one is a bit easier to check. Well, you just pick up a vector v and the scalar, say, c. Then, well, in this case, if we just compare t of, we want to compare t of cx minus c of tx, well, look at its square. I mean, look at the square of the length of this difference. And then again, by the same argument, like we write it down as the inner product of t of cx minus c of tx, comma, t of cx minus c of tx, and expanding and collecting the respective terms, what do we get? We get, okay, let me write, t of cx square minus 2 of t of cx, comma, c of tx, right? And finally, plus c of tx square. And then it's pretty straightforward to see. It's pretty straightforward to see that the result again, well, you can check. I mean, okay, so let's just move C outside. So C square of Tx, right? Square. That's the first. Then we have minus, okay, 2C square, right? Of Tx, comma Tx, and plus C square of Tx square. We see that it gives us, so eventually it gives us 0 again. So again, I mean, by the same, well, the same argument, we just obtained that, so there's certain vector so that its square of the length is 0, so the vector itself must be 0. So T of Cx minus C of Tx is 0. And therefore, we check the last property for being, we finished checking the last property for being a linear operator. Okay, so T is a linear operator, and as I said, we already checked that this is orthogonal, so it is an orthogonal linear operator. Okay, so maybe the last step, actually, if I go back to the theorem, let me also mention that there's one extra important statement, that we basically must have a unique orthogonal operator. So this orthogonal operator has to be unique in this presentation, as well as the translation has to be unique. Yeah. Or another way to say this, if you are given a rigid motion and you want to write it down as a composite of an orthogonal operator followed by a translation, so this presentation is unique. So why is it so? So that's pretty straightforward to see. So uniqueness. Well, again, suppose that there are two different presentations. So suppose that there are two different translations, so G and G prime, which basically any translation corresponds to a vector, right? So say here's U0 and here's V0, translation by U0 and V0. Translations by U0 and V0 respectively. And also suppose that we have two orthogonal operators, say T and U are orthogonal operators. And then, well, suppose that our rigid motion can be written down in two different ways. Like first, you compose T and G, and the second, you just first compose U with G prime. Well, then we can just write it down. So this expression is just G applied to T of X. So this is just T of X. And then you apply translation by U0. And this one is just U of X. And then you apply translation by V0. Right? And this, of course, holds for all V, for all X from V. Now, well, let's just substitute. Say, well, let's just look at this. Well, just substitute X equals 0 in these equalities. What do we get? So if X is 0, then what? Look, I mean, then T of 0 plus U0 must coincide with U of 0 plus V of 0, right? But T and U are linear operators. So T of 0 is 0, U of 0 is 0, so this would imply that U0 is V0, right? So meaning that this translation is the same. It has to be the same. But if the translation is the same, well, so meaning that U0 is V0, then of course, since t of tx plus u0 is the same as ux plus 0, we conclude immediately that t of x is the same as u of x for each x. And that, of course, means that t is u. Then the orthogonal operators must also coincide, right? So it shows the uniqueness. So there are no different presentations like this. All of them have to coincide with each other. Okay, so that's it. This finishes the proof of our theorem. Okay, is there any question? Is there any question? Now let me state the following application. So like now we would like to describe rigid motions on the plane in R2. So that's the following lemma. So let's see, be an orthogonal operator. And so say on R2. So that's a particular example, R2. And say let A be its transformation matrix with respect to the standard basis. So we know that such a matrix is orthogonal, right? So it satisfies the condition A times A transpose is the same as A transpose times A is the same as the identity matrix. Well, then exactly one of the following conditions is satisfied. So then, well, there are actually two choices. That's what I'm saying, right? There's two choices for T. First choice is T is a rotation. So any orthogonal operator on R2 can be one of two. Either it's a rotation with a determinant 1. So determinant of the respective matrix is 1. Or if it's not a rotation with such a determinant, then T has to be a reflection. So what's a reflection? Reflection is just a reflection about the line that passes through the origin, right? About a line through the origin. In which case, the determinant has to be -1. Okay, so basically this fact just tells us how to describe all orthogonal operators on a plane, right? So it's either of type A or type B, or no other way. So well, let's prove this. So first of all, so since T is an orthogonal operator, well, it preserves the orthonormal basis. So it preserves the standard basis. So the standard basis, if you apply T to the standard basis, then this basis T of E1, T of E2 has to be again an orthonormal basis. Is an orthonormal basis. Right? Moreover, okay, so T of E1 is a unit vector, so it has length 1 because it's a normal basis, it's orthonormal basis. And so since, let me write it, since T of E1 is a unit vector, and it is orthogonal to T of E2, well, then there are not so many possibilities. Then there are only two possibilities. Only two possibilities for T of E2. Well, why? Okay, so let me just draw a picture. So say this is my vector T of E1. And then look, I mean, T of E2 has to be orthogonal to T of E1. Well, if it's a good question, could we also have a third case C where T is a composition of A and B with determinant -1? Well, we will actually, we will see what will happen in a minute, right? About this third case, okay? Right, so let me still finish this, explaining how these two cases appear. Well, okay, so let's look at this case. Okay, so T of E1, right? And for T of E2, it must have also length 1, so it's a unit vector as well. And it must be orthogonal to T of E1. So indeed, there are only two possibilities for that, right? What? I mean, either this one, T of E2, right? Or say this one, T of E2. There are no other options because it has to be on the plane. It has to be orthogonal to T of E1 and it must have length 1. Okay. So good. So now, well, let's just look at these two cases. Okay. And okay, perhaps what I would like to do, yeah, so well, let's just maybe put the coordinates. Of course, so here say the angle is, well, let's just take an angle, say theta. And that's an angle between 0 and 2 pi, of course, right? And that's a unit vector, so it must have this coordinate. So cosine of theta, comma, sine of theta. Yeah. Yes, now for these two vectors, for this and this, there are two, so there are two options. So what are the coordinates of this? So it's either okay, so first of all, what are the coordinates? Well, what is this angle? Well, this angle is pi minus theta, right? And this angle is clearly pi over 2 because they are orthogonal, so 90 degrees. Yes, okay. And so what are the coordinates of pi of this one? Well, so in this case, we have to do what? So it's minus sine theta, right, comma, cosine theta in that picture. And for this vector, what do we have? We have sine of theta and minus cosine of theta. Yeah, that's pretty easy to see because if you substitute these angles, it's okay. Yeah, so these angles, and this is pi over 2, right? You will, if you substitute, you'll get precisely the formulas for the coordinates like this. Okay, so now, well, let's just look at the first case. So T of E2 is minus sine theta cosine theta. Well, in that case, what's a matrix? We can write down the transformation matrix, right? Because what we need to do, we just need to look at T of E1 and T of E2 and write down them as columns. And this gives us precisely, so T of E1 is cosine theta sine theta, and T of E2 minus sine theta cosine theta. This is a transformation matrix, right? And this is indeed, if you look carefully, if you look at this matrix, you will see the rotation. So this is a rotation by theta around the origin, right? And the determinant of A is clearly 1. So as you see, in this way, we will get the first case, right? And what about B? Well, the B case you will get if you have the second option for this T of E2, namely, if this is just a sine theta, comma minus cosine theta. Well, in this case, the matrix will be, so the first column stays. However, the second one changes its sign. Sine theta, cosine theta minus. And in this case, it's clearly, so what's the determinant of this? So the determinant of A is -1. And if you look carefully at what's going on with this guy, so this one, what it does, what such a matrix does with the vectors? Well, this is the reflection about the line L about the line L. So the line L has the angle theta divided by 2. With the angle between L and OX equals theta over 2. Yeah. And yes, as I said, the determinant is clearly -1. Well, let's look. Yeah, so that's what's happening, right? Well, if you just, well, you can even draw it. I mean, say for instance, this is E2, and then this E2 goes to this T of E2, and that's clear. Well, on the picture, it's clear that this is just a reflection with respect to this line. So this is theta divided by 2. Okay. So that's it. This finishes the proof. So indeed, there was a question about, yes, could we have a third case? And then this question was answered indeed. Yes, we can rotate it, yes. Okay, so, right, so let me immediately state the following consequence. So any rigid motion in R2 is either a rotation followed by a translation or it is a reflection about the line through the origin followed by translation. So there are only two options available. Well, maybe let me finish by saying that you can actually do a little bit better, but maybe I'll just mention this. What you can also show is that any rotation can be written as a composite, of at most 2 reflections. Okay, so indeed, what you can always do, you can always split your rigid motion into the composite of reflections followed by translation. Okay. So that's it. That was the last. That was the last thing I wanted to say. Okay, so let me